one time or another, most of us have been exposed to some basic education on the fundamentals of electricity. However, remembering these fundamentals and applying them is like remembering math, or history, or Latin. It's apt to slip away from you unless you use it regularly. That's why last month's tech session, Understanding Electrical Systems, was devoted to a review of circuit fundamentals. But understanding the behavior of electricity is only half of what you have to know to solve electrical problems. You also have to understand how electrical troubleshooting tools work and how to use them. Here are the electrical test tools found in many service departments. These include jumpers, test lights, voltmeters, ammeters, ohmmeters, special purpose meters, hydrometers, and service manuals. Actually, there are only three basic kinds of electrical problems. The most common of these is a circuit that's completely dead. The next most common category is the kind of trouble that blows a fuse. The last classification covers electrical circuits that operate after a fashion, but not as well as they should. Let's start with the simplest kind of trouble, a dead circuit. The problem could be an open circuit or a bad electrical unit, like a compressor clutch. All you need to track down an open circuit is a test light. Simply connect one lead of the test light to a good ground. Touch the other lead to any terminal in the circuit that's supposed to be hot. If the test light lights, the circuit is complete up to that point. Continue checking each terminal and connector in the circuit until you reach a point where the light doesn't light. The break, or open, is between this point and the last point checked. A test light and a wiring diagram is all you need to solve most garden variety circuit problems. The wiring diagrams in your service manuals provide you with the circuit information and wire color codes you'll need to trace the circuit through the wiring harness and connectors. The second basic kind of problem is a short circuit that keeps blowing fuses or causes a circuit breaker to open. This could be a short to ground in the circuit itself, or the electrical unit served by that circuit could be shorted. In a case like this, the first step is to disconnect the unit served by the circuit. If the circuit breaker stops cycling, or a new fuse doesn't blow, the trouble is in the unit and not in the circuit. However, if disconnecting the unit doesn't solve the short circuit problem, the trouble is in the circuit itself. Chances are there's a short to ground somewhere along the line. A circuit that is protected by a cycling type circuit breaker can usually be checked out with a test light. The light will blink on and off at each point checked upstream from the short to ground. It won't light, or will be very dim, downstream from the short. Upstream and downstream are very handy words for explaining electrical troubleshooting. Let's make sure everyone understands what they mean. Upstream in a circuit is simply from the short toward the source of electricity, in this case toward battery positive. Downstream is between the short and the ground side of the circuit, or battery negative. Now back to our short problem. Checking out a short that keeps blowing a fuse is somewhat different from checking a circuit protected by a circuit breaker. If a new fuse blows after disconnecting the unit, the trouble is in the wiring. The trick here is to supply voltage to the circuit without blowing the fuse or burning up the wiring. You can do this by substituting a cycling type circuit breaker in place of the fuse. Then, use your test light the same way you would in troubleshooting a circuit normally protected by a circuit breaker. When connected upstream of the short, the test light will blink on every time the circuit breaker closes. Just remember, the test light is connected in parallel with the short to ground, so your test light may not glow very brightly. That's because the short offers less resistance to ground than the test light. Another way to track down short circuits is to use a special short finder. This consists of a circuit breaker and an induction type ammeter. You'll find a detailed explanation of how this tool works in your reference book. A jumper is also a handy troubleshooting tool. Use it to bypass a unit or a portion of a circuit. For example, the engine cranks and starts, but stalls as soon as the ignition key is released to the run position. Try connecting a jumper across the ballast resistor. If this temporarily solves the problem, there is an open in the ballast resistor, so replacing it will correct the problem. A jumper can also be used to feed a circuit directly. For instance, suppose the engine doesn't crank and you suspect the ignition switch. A jumper connected between the battery and the ignition terminal of the starter relay eliminates the ignition switch and its circuit. If the engine cranks the trouble is in the ignition switch or circuit, not the relay or starter. High resistance in the ground side of a circuit is a frequent cause of electrical problems, particularly in older cars. For example, a dim light may mean a bad ground. You can check this out quickly by substituting your jumper for the ground circuit. Open circuits and short circuits are the easiest kind of troubles to understand. In the case of an open circuit, the electricity simply doesn't get to the unit it's supposed to supply. In the case of a short to ground, it takes a shortcut back to the ground side of the battery. Jumpers, test lights, a troubleshooting circuit breaker, wiring diagrams, and a working knowledge of electricity are all you need to solve most open and short circuit problems. But what about the third type of problem, where there's a complete circuit of sorts, but things aren't working the way they should? These are the problems that get into the area of electrical measurements and performance diagnosis. The basis of this type of electrical diagnosis is accurate electrical measurements. If you understand how electrical measuring instruments work, you'll find it much easier to connect them and read them correctly. The basic working parts of voltmeters, ammeters, and ohmmeters are the same or very similar. These instruments have a permanent horseshoe-type magnet, a movable coil, and pointer. However, the internal circuitry is quite different for each of these instruments. Voltmeters and ammeters differ primarily in the way the test leads are connected to the movable coil. In a voltmeter, the windings of the movable coil are connected to the test leads through a high resistance. This resistance unit limits the amount of current that is allowed to flow through the meter. When the voltmeter leads are connected across a battery or circuit, current flow through the windings of the movable coil produces a magnetic field. The north pole of this magnetic field is fairly close to the north pole of the horseshoe magnet. Since two north poles repel each other, the coil and the pointer move any time current flows through the windings of the coil. The higher the voltage, the greater the current flow, the stronger the magnetic field, and the greater the movement of the coil and pointer. A voltmeter is connected across a circuit without disconnecting any wires. In other words, it is connected in parallel with some part of the circuit. The high resistance built into the voltmeter keeps current flow through the meter low. This protects it from overheating and damage. If the two voltmeter leads are connected across 2 points in a circuit, the meter registers the voltage drop between these 2 points. Here, there is a voltage drop between the cable terminal and battery post. This means high resistance, since there should be no measurable voltage drop at this connection. If one voltmeter lead is connected to a terminal in a circuit and the other lead is connected to ground, the meter will register the voltage available at that terminal. Mechanics sometimes connect a voltmeter in series with the negative battery post and the ground cable. This won't hurt the meter, but it won't help you solve circuit problems unless you understand what the readings indicate. Explaining these readings would gobble up 5 minutes of our film, so we've covered it in the reference book. An ammeter, like a voltmeter, has a permanent horseshoe-type magnet, a movable coil with pointer attached and a scale. However, its internal circuitry is entirely different. The external test leads are connected to a low-resistance bus bar or shunt. The leads to the movable coil are connected in parallel with this low-resistance shunt. A shunt is nothing more than a parallel circuit. When the ammeter is connected into a circuit, most of the current flows through the low resistance of the shunt. Only a very small amount flows through the much higher resistance of the movable coil windings. An ammeter must always be connected in series, so that all of the current flowing in the circuit flows through the ammeter. That means you must disconnect at least one wire to connect an ammeter correctly. Never connect an ammeter across a circuit, the way you connect a voltmeter. If you connect an ammeter in parallel, you'll fry it for sure. That's why you must connect an ammeter in series. Before connecting an ammeter, make sure there's enough resistance in the circuit you're testing to limit the amount of current flowing through the circuit and the meter. Unlike the voltmeter, an ammeter doesn't have enough internal resistance to protect itself against excessive current flow and serious damage. Be sure and use an ammeter with a high enough capacity to handle the flow in the circuit you're testing. The ohmmeter is a relatively delicate instrument. It is used to obtain precise resistance measurements. It's used frequently by electronic technicians, but is used far less frequently for checking automotive circuits. Unless you want to measure the exact resistance of an electrical component, like a resistance-type ignition cable, you won't need an ohmmeter. An ohmmeter is actually a voltmeter that's been calibrated to read ohms instead of volts. It has its own supply of electricity, usually small batteries mounted in the ohmmeter. These batteries have a known voltage and are used to send a small test current through the circuit or electrical unit being tested. The circuit or electrical component being tested must be dead when using an ohmmeter. Never, never, never connect an ohmmeter into or across a hot circuit. A voltmeter and ammeter handle just about any type of automotive circuit troubleshooting you're apt to run into. Actually, a voltmeter gives you an indication of resistance by telling you how much the resistance in the circuit reduces the voltage. Except when you're tracking down simple troubles like open or short circuits, the battery should always be checked and in good shape before you start testing or making electrical measurements. You can check a battery in one easy step if it's in good condition. You'll have to make 2 tests if its condition is questionable. The first step is to check the state of charge by measuring the specific gravity or concentration of the electrolyte. The principle is simple. The more acid there is in the electrolyte, the higher the state of charge, and the higher the hydrometer float will rise in the test sample. The most important part of your hydrometer test is noting any differences between cell readings. If all cell readings are uniformly low, the battery simply needs to be recharged. A sizable difference between cell readings means you should load test the battery. This test checks the battery's ability to deliver electrical power. It determines whether or not the battery is still serviceable. The battery load tester includes a voltmeter, an ammeter, and an adjustable load or resistance. Hookup connections are described in the instructions that come with the tester. You'll find a lot more information on battery service and circuit testing in this month's reference book. And don't forget that those wiring diagrams in your service manuals are one of your most valuable electrical troubleshooting tools. The next time you run into an electrical problem, don't duck it or just wiggle wires and hope. Get out your troubleshooting tools and tackle the problem scientifically.